Tonight we're exploring the most chilling thought experiment in physics. What happens if our sun simply vanishes? Not gradually dimming or exploding. Just gone, erased from existence as if someone flipped a universal switch. What we're about to discover will change how you think about survival itself. For exactly 8 minutes and 20 seconds, Earth would continue its morning routine, completely unaware its energy source had disappeared. Then everything changes. We'll follow the cascade transforming our planet from a warm, living world into a frozen wanderer. You'll see humanity's desperate final strategies for survival in a universe that suddenly became utterly hostile. From those eerie first minutes to the gradual shutdown of every system sustaining life, this journey reveals something extraordinary. Just how fragile our everyday existence truly is. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Sunlight streaming through your window left the sun's surface 8 minutes and 20 seconds ago. That seemingly simple fact contains physics' most unforgiving truth. Nothing travels faster than light, not even catastrophe. If our sun vanished this very moment, Earth would continue its morning routine. Perfect normalcy would reign. Coffee shops would serve their rush hour crowds. Solar panels would keep generating electricity from light that no longer had a source. Children would play under sunshine that had become orphaned, racing across the void with nowhere to return. The physics governing this cosmic delay operates with clockwork precision. Light moves at exactly 299,792,458 meters per second. Not approximately, but exactly. This represents a fundamental speed limit even disaster cannot violate. When those final photons leave the sun's surface, they carry something precious. The last energy our planet will ever receive from its parent star. What makes these 8 minutes so unsettling is their perfect ordinariness. Traffic lights change from red to green. Planes taxi on runways preparing for flights that will never complete. Weather forecasters predict sunny afternoons that will never arrive. The last generation of sunbeams paints Earth's surface with golden morning light. Meanwhile, deep space already holds a terrible secret. No living thing yet knows. Earth would be living on borrowed time. Literally, every ray illuminating our world represents the universe's most generous loan. Energy that traveled across the void to sustain a planet whose power source had already vanished. When that final photon reaches Earth's atmosphere, the most dramatic transformation in our planet's history begins. Imagine flipping a light switch in reverse. Instead of darkness becoming light, blazing daylight becomes absolute night. At precisely 8 minutes and 20 seconds after the sun's disappearance, Earth's daylight simply vanishes, as if someone threw a switch controlling the universe's master electrical system. Cities worldwide suddenly find themselves illuminated only by artificial lights. Street lamps blink on in bewildered response to light sensors detecting the impossible. The sky transforms into something no human has ever witnessed. A black canvas pierced by thousands of stars, suddenly visible in broad daylight. The moon appears as a faint gray disk reflecting only starlight. Venus and Jupiter emerge as brilliant points no longer washed out by solar glare. Automatic systems respond with mechanical confusion. Streetlights from Tokyo to New York flicker to life. Solar-powered devices shut down mid-operation. Their energy input drops from blazing sunshine to absolute zero in a single moment. Millions of artificial lights create an eerie urban aurora, cities glowing against star-filled darkness like scattered islands of human defiance. The human response unfolds in waves of disbelief. Office workers crowd windows, staring at skies revealing the cosmos with crystal clarity. Parents gather children close, struggling to explain something without precedent. Air traffic controllers face managing flights in perfect darkness. Pilots navigate by stars in what should be sunny afternoon. Perhaps most haunting is the silence that follows initial confusion. No gradual dimming prepared anyone for this. No weather phenomenon explains sudden stars where the sun should reign. In those first minutes after darkness falls, humanity collectively realizes something profound. They're witnessing something that redefines catastrophe itself, the moment Earth became an orphan planet. What would you feel if the world's lighting suddenly changed completely? 1 second, children squint against bright sunlight on school playgrounds. The next, they stand beneath a canopy of stars visible in perfect detail. The lighting change doesn't happen gradually like twilight. It's instant. Binary. Like someone replaced the cosmic light bulb with a completely different fixture. Earth's new illumination comes from sources never meant to light a daytime world. The brightest star in our sky, Sirius, provides roughly 1/10 billionth of the light our sun delivered moments before. Venus shines like a cosmic lighthouse, but it offers less illumination than a single candle. The full moon, when visible, glows with the brightness of a dim street lamp viewed from blocks away. This dramatic lighting shift creates a world of impossible contrasts. Skyscrapers cast sharp shadows under artificial lights. Their upper floors disappear into star-pierced blackness. Car headlights become the primary source of road illumination, even at what should be high noon. Emergency generators kick in across the globe. Light sensors mistake cosmic darkness for nightfall system-wide. Photography equipment around the world suddenly captures images stolen from science fiction. Time-lapse cameras recording city traffic reveal streams of headlights, flowing through streets beneath star fields that stretch to every horizon. Security cameras switch to infrared mode. Their light sensors register illumination levels normally reserved for midnight. The psychological impact proves just as striking as the visual transformation. Humans evolved to associate starlight with rest, darkness with danger, sunlight with safety and activity. Now the cosmic schedule has been permanently scrambled. Children point at constellations visible in the middle of their lunch break. Adults struggle to process a reality where daytime stargazing has become the new normal. Picture the world's electrical systems suddenly losing a quarter of their power. Within minutes of the cosmic lights going out, Earth's power infrastructure begins fighting a losing battle. Solar panels spanning from residential rooftops to massive utility installations suddenly contribute exactly 0 watts. In regions heavily dependent on solar energy, power companies watch their generation capacity plummet instantly. California's electrical grid operators experience the crisis first. The state generates over 30% of its electricity from solar installations during peak daylight hours. Grid computers detect the impossible drop in power generation. They automatically trigger emergency protocols. Backup natural gas plants receive urgent startup commands. Nuclear reactors already running at baseline capacity cannot increase output fast enough. The shortfall becomes a mathematical nightmare. Meanwhile, satellites orbiting overhead begin their own desperate countdown to silence. The International Space Station relies on massive solar panel arrays that normally collect abundant energy during sunlit portions of each orbit. Now those arrays collect nothing. The station switches to battery backup systems designed to last through normal shadow periods, not permanent darkness. Astronauts aboard have perhaps 6 to 8 hours of full power remaining. Communication satellites face identical crises: weather satellites, GPS satellites, internet backbone satellites, all begin systematically shutting down non-essential systems to preserve battery life. Ground controllers scramble to prioritize which satellite functions matter most. Navigation systems get priority. Entertainment satellites get sacrificed. The cascade of power failures creates a technological apocalypse racing around the globe. Power grids strain under sudden load imbalances. Rolling blackouts spread across regions where renewable energy infrastructure had been counted on for grid stability. Emergency battery systems designed to last hours or days now face the prospect of running forever. Have you ever wondered what would happen if every astronomer on Earth detected the impossible at once? At observatories scattered across 6 continents, automated detection systems begin triggering alarms that were never supposed to activate. The Palomar Observatory in California, the Very Large Telescope in Chile, the Mauna Kea Complex in Hawaii, radio telescopes from Australia to South Africa. Within minutes of the sun's disappearance, every major astronomical facility on Earth registers readings that violate fundamental expectations about how the universe operates. Solar monitoring satellites orbiting near Earth detect something unprecedented. The Solar and Heliospheric Observatory, positioned 1.5 million kilometers toward the Sun, records the impossible. The moment our star simply ceases to exist, no explosion, no gradual dimming, no preliminary warning signals. The spacecraft's instruments register a transition from normal stellar output to absolute zero. Across all electromagnetic wavelengths, mission scientists stare at data readouts that suggest catastrophic instrument failure. Except every independent sensor confirms the same impossible result. Ground-based observatories face their own crisis of disbelief. Telescopes pointed at the sun's location detect nothing but the background star field visible behind our former star's position. Solar physicists who spent careers studying magnetic field patterns suddenly confront instruments measuring empty space. Emergency communication networks activate across the global scientific community. The International Astronomical Union triggers protocols designed for detecting potentially hazardous asteroids. Except this emergency dwarfs every disaster scenario scientists had ever considered. Within 2 hours, the world's leading astrophysicists agree on a conclusion that challenges everything humanity thought it knew about stellar evolution. The sun hasn't burned out or exploded or collapsed into a black hole. It has simply vanished from existence. The scientific community faces an unprecedented challenge. How do you issue emergency warnings to 7 billion people about an impossible cosmic event that threatens the continuation of life itself? You're a passenger in a car that suddenly loses its steering wheel, brakes, and engine all at once. That's essentially what happens to Earth the moment our sun vanishes. Our planet doesn't gently drift away or gradually slow down. It immediately becomes a runaway cosmic projectile, hurtling through space in whatever direction it happened to be traveling at that precise instant. Earth rockets away from our former solar system at exactly 67,000 miles per hour. That's roughly 30 kilometers per second, fast enough to circle our planet's entire equator in just 22 minutes. This breakneck speed isn't some new cosmic acceleration. It's simply the orbital velocity we've maintained for 4.6 billion years. Suddenly freed from the gravitational leash that kept us circling our star. Like a cosmic dog whose chain just snapped, Newton's first law of motion governs our planet's new trajectory with merciless precision. Objects in motion stay in motion unless acted upon by an external force. For billions of years, the sun's gravity provided that external force, constantly pulling Earth away from straight-line motion into our familiar elliptical orbit. Remove that gravitational influence. Earth simply continues whatever motion it possessed the moment of solar disappearance. The direction of our cosmic escape depends entirely on random timing. If the sun vanished while Earth sat at the closest point of our orbit, we'd head roughly toward the constellation Sagittarius. Disappearance during our most distant orbital point would send us careening toward Gemini. Pure cosmic lottery determines which direction our planet will wander, potentially for millions of years through the frozen darkness of interstellar space. What makes this scenario particularly unsettling is the complete absence of any mechanism to slow down. No cosmic brakes exist in the vacuum of space. No stellar traffic cops wait to redirect runaway planets. Earth becomes a permanent exile, traveling at highway speeds through a universe where the nearest potential new home lies trillions of miles away. While Earth rockets away from our former solar system, something remarkable happens with our closest cosmic neighbor. The Moon doesn't get left behind or wander off on its own trajectory. Instead, it joins Earth on what becomes the ultimate buddy road trip through interstellar space. For once in this cosmic disaster scenario, the laws of physics actually work in our favor. The Moon orbits Earth at roughly 2,400 miles per hour relative to our planet's motion. When the Sun vanishes, both Earth and Moon were already traveling together at 67,000 miles per hour around our former star. Losing the Sun doesn't suddenly break the gravitational bond between Earth and its satellite. The Moon simply continues its faithful dance around our planet. Both of them hurtle through space as a single gravitational unit. Think of it like two ice skaters spinning together when the music suddenly stops. They keep spinning around each other even as they glide across the rink in whatever direction their momentum carries them. This gravitational loyalty provides one of the few sources of stability in our planet's otherwise catastrophic situation. Ocean tides continue their regular rise and fall, driven by the Moon's unchanged gravitational influence. Earth's axial tilt remains stabilized by our satellite's presence, preventing wild wobbles that could make climate conditions even more chaotic. The Moon even maintains its gradual drift away from Earth, currently about 1.5 inches per year. It has done so for billions of years. This slow separation continues because the physics governing tidal friction operates independently of our former solar orbit. In a universe suddenly gone hostile, at least one cosmic relationship remains dependably intact. Our satellite becomes Earth's permanent, traveling companion on a journey that could last millions of years, while our planet transforms into a frozen ball drifting through interstellar darkness. The Moon continues its eternal watch. It is a loyal cosmic guardian, maintaining the rhythms that have defined Earth's relationship with its closest neighbor since both worlds were young. What happens when a family that's lived together for 4.6 billion years suddenly scatters forever? The solar system's planetary family experiences its final breakup with shocking swiftness. Within hours of the Sun's disappearance, Jupiter, Saturn, and Mars each head toward different constellations. Each planet becomes a lonely wanderer, carrying nothing but gravitational memories of the cosmic home they'll never see again. Jupiter, our solar system's gentle giant, becomes perhaps the most poignant exile of all. This massive planet has spent its entire existence serving as the cosmic vacuum cleaner. It uses its immense gravity to capture or deflect asteroids and comets that might otherwise threaten inner planets like Earth. Now Jupiter wanders alone through interstellar space. Its protective services are no longer needed by the planetary siblings it left behind. The gas giant takes its entire retinue of moons on this cosmic exile. Europa, with its hidden ocean beneath an icy shell, continues orbiting Jupiter, even as both travel through the frozen darkness between stars. As volcanic activity persists, driven by tidal heating from Jupiter's gravity rather than solar energy. The entire Jovian system becomes a miniature solar system wandering through the galaxy. It is a gravitational family that maintains its internal bonds. The larger planetary family scatters forever. Saturn faces its own melancholy journey through space. Its magnificent ring system slowly sublimates away in the absence of solar radiation. The rings that have defined Saturn's identity for millions of years will gradually dissipate over cosmic time. This leaves the planet naked and unadorned as it wanders through stellar exile. What makes this planetary dispersal particularly striking is its randomness. Planets that shared the same cosmic zip code for billions of years now head in completely different directions. This is based purely on where they happened to be in their orbits when disaster struck. Earth's journey into true cosmic exile unfolds with surprising patience for such a dramatic event. Our planet requires roughly 60 days to travel the 93 million miles. This is what astronomers call one astronomical unit, or AU. It once separated us from our vanished sun. This means Earth takes 2 full months to reach the empty point in space. Our star used to anchor the entire solar system there. By this milestone, any remaining solar panels have long since stopped generating power. The feeble energy storage in Earth's atmosphere has dissipated into space. Global temperatures have plummeted to levels that make Antarctica's worst winter feel tropical. Yet Earth continues its methodical journey outward. It passes the former orbital paths of Mars, then Jupiter, then Saturn, like a cosmic tourist visiting the abandoned campsites of former neighbors. The real milestone comes roughly to 5 years after our solar exile begins. Earth reaches the outer boundary of what once was our solar system. It is a region called the Kuiper Belt. It is populated by icy bodies and dwarf planets like Pluto. They orbited our former sun in the cold outer suburbs. Now these frozen relics scatter in all directions. Each one follows its own trajectory into interstellar space, like cosmic tumbleweeds blown apart by the ultimate stellar wind. At this point, Earth officially enters the space between stars. It is a region so empty that matter density drops to less than 1 atom per cubic centimeter. The nearest star lies over 4 light-years away. We travel at our current breakneck pace of 67,000 miles per hour. Reaching that distant stellar neighbor would require roughly 40,000 years. Earth has become an interstellar wanderer on a journey measured in geological timescales. What's remarkable about this migration is how methodical it appears from the outside. Any alien astronomer observing our situation would see a planet maintaining steady velocity through space, while gradually cooling from its stored heat. The solar system's smaller residents create their own chaotic celebration of cosmic freedom. Millions of asteroids that spent billions of years behaving like well-ordered citizens suddenly transform into cosmic confetti. They scatter in every possible direction by the loss of their gravitational overseer. The asteroid belt ceases to exist within days of the Sun's disappearance. That orderly collection of rocky debris orbiting between Mars and Jupiter simply vanishes as a coherent structure. These space rocks, some the size of mountains and others no bigger than school buses, each become independent travelers. They follow their own random vectors into the infinite. Ceres, the belt's largest resident and technically a dwarf planet, heads off toward interstellar space, like a cosmic bowling ball that finally escaped the lane bumpers. Comets experience perhaps the most ironic fate of all. These dirty snowballs from the outer solar system built their entire identity around spectacular visits to the inner solar system, where solar radiation would heat their icy surfaces. This creates magnificent tails visible from Earth. Now they wander through space without any star to provide the heat needed for their signature light shows. They become invisible nomads. They carry their frozen potential for beauty through a universe where no audience will ever witness their spectacular displays. The situation grows even more poetic when you consider the Oort cloud. It is a spherical shell of icy objects that extends roughly halfway to the nearest star. This collection of potential comets, numbering in the trillions, was gravitationally bound to our Sun by the most tenuous invisible threads. When those threads snap, the Oort cloud doesn't just disperse. It essentially evaporates into interstellar space like cosmic steam rising from a pot. Some of these liberated space rocks will eventually encounter other star systems during their million-year journeys through the galaxy. Alien astronomers might detect them as mysterious interstellar objects. They are cosmic visitors carrying chemical signatures of a stellar system that no longer exists. In a sense, these scattered asteroids and comets become the only messengers capable of telling the universe something important. They show that our solar system once existed, before catastrophe transformed an orderly planetary family into cosmic refugees scattered across the galaxy. Earth's transformation from habitable planet to cosmic S-cube doesn't happen overnight. But it doesn't take long either. Within the first week of solar abandonment, our planet's average temperature crashes. It falls from a comfortable 59 degrees Fahrenheit to a bone-chilling minus 20 degrees Fahrenheit. That's a 79-degree plunge in just 7 days, equivalent to moving from Miami Beach to the frozen tundra of northern Alaska in the span of a single week. The physics behind this rapid cooling operates with ruthless efficiency. Earth receives virtually all its energy from solar radiation that has suddenly been cut to absolute zero. Meanwhile, our planet continues radiating heat into space at the same steady rate it always has. It's like someone turned off the furnace while leaving all the windows wide open, during a cosmic blizzard that never ends. Different regions of Earth experience this thermal collapse at dramatically different rates. Tropical areas, which stored the most solar energy in their atmosphere and oceans, initially resist the cosmic freeze more successfully than polar regions. But even the Sahara Desert begins experiencing nighttime temperatures that would make penguin colonies shiver. Cities like Phoenix and Las Vegas, built for blazing heat, suddenly face Arctic conditions, without any infrastructure designed for extreme cold. Ocean surfaces provide temporary thermal relief, like a planetary heating pad slowly losing its warmth. The vast heat capacity of seawater means coastal regions cool more gradually than inland areas. But this advantage proves temporary. The ocean's stored energy represents a finite battery, discharging into space without any possibility of recharging. Every day brings temperatures that would have been record-breaking cold snaps under normal circumstances. By day 7, the global average temperature has dropped below the freezing point of water. This marks the beginning of the end for Earth's surface water cycle. Rivers in temperate regions begin developing ice shells. Lakes start their transformation into solid skating rinks. 4 weeks after losing our solar heating system, Earth reaches temperatures so extreme that the very air begins to snow. At -40 to -60 degrees Fahrenheit, something magical and terrifying happens. Carbon dioxide starts condensing directly from gas into solid crystals, creating snowfall composed of dry ice rather than frozen water. Earth's atmosphere begins precipitating itself onto the surface. Like a cosmic snow globe that's been shaken too hard, carbon dioxide snow doesn't behave like the gentle flakes that drift down during winter storms. These crystals sublimate directly back into gas when they contact anything warmer than -109 degrees Fahrenheit, creating ghostly wisps of vapor that rise from the ground like reverse snow. The effect resembles a planetary special effects show, with crystalline precipitation that disappears into fog before it can accumulate into drifts. This atmospheric snowfall marks the beginning of a fundamental change, a change in Earth's air composition. The normal mixture of nitrogen, oxygen, and trace gases that has sustained life for billions of years begins separating into distinct layers, based on their freezing points. Carbon dioxide, being heavier and more prone to condensation, starts settling toward the surface, while lighter gases remain aloft. Earth's atmosphere begins sorting itself like ingredients in a cosmic recipe that's been left in the cosmic freezer too long. Weather patterns during this phase become unlike anything in Earth's climatological history. Traditional storm systems, which depend on water vapor and temperature gradients, give way to strange new phenomena, driven by the condensation of atmospheric gases. Regions that once experienced hurricanes or tornadoes now host bizarre precipitation events, where the very air crystallizes and falls like chemical snow. The psychological impact on any surviving humans becomes profound during this atmospheric transformation. People who manage to find heated shelter and adequate food supplies must now confront a new reality. The sky itself is slowly falling. 12 months into Earth's cosmic exile, our planet reaches temperature extremes that transform atmospheric behavior in ways that seem borrowed from science fiction. At -150 to -200 degrees Fahrenheit, the very air begins changing from gas to liquid, in a carefully orchestrated sequence determined by the freezing points of different atmospheric components. Earth essentially becomes a chemistry laboratory, conducting the universe's largest phase change experiment. Nitrogen, which makes up 78% of our atmosphere, begins its own condensation dance at these extreme temperatures. Unlike carbon dioxide snow, liquid nitrogen creates visible rivers and pools of cryogenic fluid that would instantly freeze any biological tissue it contacts. These nitrogen streams flow downhill like water, except they're cold enough to shatter steel and turn rubber into glass. Earth's surface begins accumulating pools of atmospheric components that have transitioned from invisible gas to exotic liquid. Oxygen, representing 21% of our former breathing mixture, follows nitrogen into liquid form at slightly higher temperatures. The oxygen that once sustained every breath taken by every animal on Earth now drips from trees and buildings, like cosmic dew that could either support combustion or instantly freeze lung tissue. The irony becomes almost poetic. The most essential element for life transforms into a substance so cold it would kill any organism that tried to breathe it. Water vapor. The tiny fraction of atmospheric moisture that survived the initial weeks of cooling undergoes its own exotic transformation. Rather than simply freezing into ice, water vapor sublimates directly into crystalline formations that build up on every surface like intricate frost sculptures. These ice formations grow with mathematical precision, creating geometric patterns that would be breathtakingly beautiful if anyone remained alive to appreciate their alien artistry. The atmospheric pressure at Earth's surface begins dropping as more gases transition from their gaseous state. Areas that once supported normal breathing pressure now offer atmosphere so thin that any hypothetical survivor would need pressurized equipment. The most psychologically devastating milestone arrives when Earth's tropical regions become colder than the South Pole. Places like Singapore, Mumbai, and Rio de Janeiro had never experienced freezing temperatures in recorded human history. Now they register surface temperatures that would make Antarctic research stations seem tropical by comparison. The geographic rules that defined Earth's climate for millions of years have been completely reversed. Without solar energy to drive atmospheric circulation, the complex weather patterns that once redistributed heat simply cease to function. Trade winds die, ocean currents slow to a crawl. The jet stream, that high-altitude river of air that shaped weather patterns across entire continents, becomes a barely detectable whisper. In an atmosphere growing thinner by the day, Earth's climate system essentially flatlines, leaving only one significant source of energy: the heat radiating upward from our planet's molten interior. Geothermal energy, which previously contributed less than 0.1% of Earth's surface heat budget, suddenly becomes the only game in town. Hot springs and geysers that were once minor tourist attractions transform into the last oases of liquid water. On our planet's surface, Yellowstone's thermal features, Iceland's hot springs, and volcanic regions around the Pacific Ring of Fire become Earth's final warm spots. Islands of relative warmth in an ocean of cosmic cold. The temperature gradient between geothermal areas and the surrounding frozen landscape creates truly alien weather phenomena. Steam rising from hot springs instantly condenses into ice crystals, creating localized snow showers that fall upward as much as downward. Geysers shoot columns of water that freeze into fantastic ice sculptures. Before the water can return to Earth, these thermal oases become surrounded by rings of exotic ice formations that grow more elaborate with each geothermal eruption. Volcanic activity actually increases during this phase, as Earth's crust adjusts to the thermal stress of rapid surface cooling combined with unchanged internal heat. Miles beneath Earth's frozen surface, a remarkable drama of survival unfolds. In the depths where planetary heat still flows from our world's molten core, while the surface becomes a cosmic ice sculpture, temperatures just a few kilometers underground remain surprisingly warm, proof that Earth's internal nuclear furnace continues operating regardless of external cosmic catastrophe. Our planet's core doesn't care that the sun vanished. It keeps generating heat from the radioactive decay that has powered Earth's interior for 4.6 billion years. The geothermal gradient that normally increases temperature by about 50 degrees Fahrenheit for every kilometer of depth becomes Earth's most precious resource. At depths of just 6 to 10 kilometers, rock temperatures remain warm enough to support liquid water, roughly the distance of a moderate hike. These deep zones represent Earth's final refuge. Underground chambers where the laws of thermodynamics provide sanctuary from the cosmic cold. Deep groundwater aquifers trapped in porous rock layers become Earth's last liquid reservoirs. These underground lakes and rivers, heated by contact with warm rock, continue flowing in eternal darkness. They represent a hydrological cycle completely independent of surface weather, solar energy, or atmospheric conditions. Water evaporates from warm rock surfaces, condenses on cooler underground formations, flows through subterranean channels in patterns that mirror the surface water cycle that once defined Earth's climate. Certain extremophile bacteria continue thriving in these warm depths. Microscopic organisms adapted to life in Earth's deep crustal environment. These organisms have never depended on solar energy for survival. They derive their energy from chemical reactions with minerals in the hot rock, essentially eating the planet itself for sustenance. In the depths where Earth's internal heat meets trapped water and suitable chemistry, life persists, in the form of microbial communities that remain completely unaffected by the cosmic disaster. The temperature difference between Earth's frozen surface and its warm depths creates potential for extraordinary engineering solutions. Any civilization capable of deep drilling could theoretically tap into these internal heat sources to create underground habitats warmed by geothermal energy. These depths represent Earth's final frontier, not in space but beneath our feet. The moment sunlight disappears, Earth's green infrastructure begins its death spiral. Every leaf, every blade of grass, every towering redwood tree suddenly loses access to the energy source that has powered plant life for over 3 billion years. Photosynthesis simply stops. The miraculous process that transforms sunlight, carbon dioxide, and water into food ceases to exist. It's like someone cut the power cord to the planetary food factory. It has been running continuously since the dawn of complex life. Plants don't die immediately from the loss of photosynthesis alone. Most have enough stored energy in their tissues to survive for days or even weeks without producing new food. Trees, with their massive reserves of starch and sugars stored in their trunks and roots, initially seem like they might weather this cosmic storm. But photosynthesis provides more than just food. It's the fundamental engine that drives cellular repair, growth, and defense against disease. Without this energy input, plants begin failing like biological machines whose maintenance budget has been permanently canceled. The cold delivers the killing blow faster than starvation ever could. As Earth's temperature plummets below freezing within the first week, plant cell walls begin rupturing from ice crystal formation. Tropical plants, which never evolved tolerance for freezing conditions, die within days. Cellular water turns to ice and literally explodes their living tissues from the inside. Even hardy temperate species that normally survive winter find themselves overwhelmed. It is cold far more severe than their evolutionary experience prepared them to handle. Small plants and seedlings become the first casualties in this botanical apocalypse. Grasses, flowers, and garden vegetables die within days. Their delicate tissues cannot survive the combination of energy starvation and thermal shock. Bushes and shrubs follow within weeks. Their above-ground portions freeze solid, while their roots struggle with soil that's transitioning from life-supporting earth to permanent permafrost. The larger trees put up the most valiant resistance. They draw on energy reserves accumulated over decades or centuries of growth. With every photosynthesizing plant on Earth suddenly offline, our planet's oxygen factory shuts down permanently. For the first time in over 2 billion years, Earth stops producing the oxygen that every animal requires for survival. The atmospheric oxygen we're breathing right now represents the accumulated output of countless generations of plants and algae. That production line has just been permanently severed. Fortunately, Earth's atmosphere contains a substantial oxygen reserve, roughly 21% of the total air volume. This massive stockpile means humans and other animals won't immediately suffocate when plants stop producing oxygen. The atmosphere holds enough oxygen to support current breathing requirements for several years, even with no new production. But this finite supply begins depleting the moment respiration continues without any corresponding oxygen generation. Meanwhile, carbon dioxide levels begin their relentless climb toward dangerous concentrations. Every breath exhaled by every surviving animal adds carbon dioxide to an atmosphere that no longer has any mechanism for removing it. Decomposing organic matter releases additional carbon dioxide. The billions of plant corpses freezing across Earth's surface continue cellular breakdown even in the cold. The atmospheric balance that has sustained complex life for hundreds of millions of years begins tilting toward toxicity. The ocean provides a temporary buffer for both oxygen depletion and carbon dioxide accumulation. Seawater holds dissolved oxygen that can supplement the atmospheric supply. Ocean water also absorbs excess carbon dioxide from the air. But as ocean surfaces begin freezing, this gas exchange slows dramatically. The marine oxygen reserve becomes trapped beneath ice sheets. The ocean's ability to absorb excess carbon dioxide diminishes as freezing water loses its capacity for dissolving gases. Ocean phytoplankton face their own extinction crisis. Microscopic marine plants that produce roughly half of Earth's oxygen depend on sunlight filtering through ocean water to power their photosynthesis. In the permanent darkness following solar disappearance, marine oxygen production ceases just as completely as terrestrial plant production. The extinction cascade begins with Earth's herbivores, animals who discover that their entire food supply has simultaneously died. Deer, rabbits, cattle, sheep. Every animal that depends directly on plants for nutrition faces immediate starvation, as their food sources transform from living vegetation to frozen botanical corpses. Unlike the plants themselves, which stored enough energy to survive for days or weeks, most herbivores lack sufficient body fat reserves to sustain them through the extended period required to find alternative food sources. Large herbivores become the first dramatic casualties in this ecological collapse. Elephants, which require hundreds of pounds of vegetation daily to maintain their massive bodies, begin starving within days of plant death. Cattle herds that once grazed peacefully in pastures now wander desperately through frozen grasslands, searching for anything digestible among the crystallized remains of what was once their primary food source. Even smaller herbivores like rabbits and squirrels struggle to locate any plant material that hasn't been transformed by freezing into indigestible ice. Carnivores initially benefit from this herbivore die-off, enjoying an unprecedented abundance of meat as starving plant eaters become easy prey. Lions feast on weakened zebras. Wolves hunt deer herds driven to desperation by hunger. Bears emerge from their dens to discover a landscape littered with the carcasses of herbivores. Many could not adapt to sudden dietary scarcity. For a brief period, predators experience what might seem like a golden age of hunting success. But this carnivorous bonanza proves tragically temporary. As herbivore populations crash towards zero, predators face their own starvation crisis. The food web that sustained carnivores through herbivore populations collapses as dramatically as the plant foundations that supported the entire system. Predators that specialized in hunting specific herbivore species find themselves with no prey to hunt. The speed of this cascade proves shocking to any observer familiar with natural ecosystem dynamics. Earth's landscapes undergo a macabre transformation. Forests and grasslands become vast organic cemeteries. Every square mile of formerly living ecosystem now hosts the frozen remains of what was recently a thriving biological community. Trees stand like botanical tombstones in their own graveyard. Their skeletal branches reaching toward a star-filled sky that will never again provide the energy needed for spring's renewal. Meadows that once waved with grass and wildflowers become frozen archives of plant matter, preserved in cosmic cold like specimens in a planetary morgue. Decomposer organisms face their own survival crisis in these extreme conditions. Bacteria and fungi that normally break down organic matter evolved to function within normal Earth temperature ranges, where chemical reactions proceed at rates suitable for biological metabolism. At the subarctic temperatures now covering most of Earth's surface, bacterial decomposition slows dramatically, the billions of tons of dead plant and animal matter accumulating across the landscape decompose so slowly that organic material begins building up like biological sediment. Certain extremophile bacteria adapted to cold environments suddenly find themselves in paradise. These specialized organisms, which previously occupied niche habitats in polar regions and high-altitude environments, now inherit entire continents of organic matter, with minimal competition from other decomposer species. Cold-adapted bacteria begin their own population explosion, feeding on the unprecedented abundance of dead biomass, while most of their biological competitors struggle with temperatures far below their operational limits. The biochemistry of decomposition changes fundamentally under these extreme conditions. Normal bacterial processes that break down organic matter into carbon dioxide and water slow to a crawl, while anaerobic bacteria capable of functioning without oxygen begin dominating decomposition processes. These organisms produce methane, hydrogen sulfide, and other gases as byproducts of their metabolism, creating atmospheric chemistry unlike anything Earth has experienced since before oxygen-producing organisms evolved billions of years ago. While Earth's surface transforms into a biological wasteland, life persists in one of the planet's most alien environments. The deep ocean thermal vents scattered across the seafloor thousands of feet below the surface. These underwater oases have never depended on sunlight for energy. Instead, they're powered by Earth's internal heat and chemical processes that operate completely independently of solar radiation. As the last bastions of active life on our frozen planet, these thermal vent communities represent evolution's most remarkable backup plan. Deep-sea thermal vents create their own energy through chemosynthesis, a process that harnesses chemical reactions instead of sunlight to produce food. Bacteria living around these underwater hot springs derive energy from hydrogen sulfide, methane, and other chemicals spewing from Earth's interior. These chemosynthetic bacteria form the foundation of entire ecosystems. That includes giant tube worms, ghostly white crabs, and bizarre fish species that have never seen sunlight. While surface life dies from cold and starvation, thermal vent communities continue their ancient metabolic processes. As if nothing had changed, The thermal energy that powers these communities comes directly from Earth's molten interior through underwater volcanic activity. Superheated water enriched with dissolved minerals erupts from the seafloor, creating underwater geysers that maintain temperatures of several hundred degrees Fahrenheit. Even as the ocean surface above freezes solid, this geothermal energy provides a heat source that will continue operating for millions of years, long after Earth's surface has become a permanently frozen world. These deep-sea communities exist in perpetual darkness anyway, so the loss of sunlight doesn't affect their daily operations. Organisms adapted to life around thermal vents have evolved sensory systems based on chemical detection and pressure sensitivity rather than vision. They navigate their world through methods that remain fully functional regardless of cosmic lighting conditions. The isolation of these thermal vent communities becomes their greatest survival advantage, protected by miles of ocean water from surface temperature changes. These deep-sea ecosystems continue functioning, even as the ocean surface develops thick ice coverage. The thermal vents essentially become Earth's biological arcs, preserving examples of complex life in underwater sanctuaries that could potentially survive for geological timescales. While the rest of Earth's biosphere faces extinction, these chemical-powered communities represent our planet's final strongholds. Earth's atmosphere doesn't surrender to cosmic cold all at once. Instead, it stages a strategic retreat that unfolds over months and years. Different regions experience atmospheric liquefaction at dramatically different rates, depending on their unique thermal characteristics. It's like watching a planetary-scale game of freeze tag. In this game, geography determines which areas get tagged first by the advancing cosmic winter. Polar regions lead this atmospheric transformation. They have already experienced the most extreme cooling during Earth's first weeks without solar energy. At the North and South poles, atmospheric components begin their phase transitions from gas to liquid and solid within months of the sun's disappearance. These regions become Earth's testing laboratories for atmospheric chemistry under extreme conditions. They preview the fate that awaits the rest of the planet. Coastal areas resist atmospheric liquefaction longer than inland regions. The ocean's massive thermal mass provides temporary protection against the cosmic freeze. The Atlantic and Pacific coastlines maintain gaseous atmospheres for additional months compared to continental interiors. In continental interiors, atmospheric gases begin condensing more rapidly. This creates a patchwork of atmospheric states across Earth's surface. In some regions, people might still breathe normally. In others, the very air has begun raining out of the sky. Mountain regions experience their own unique atmospheric behavior during this transition. High-altitude areas, already accustomed to thin air and cold temperatures, witness atmospheric liquefaction beginning at their peaks. It gradually descends toward valley floors, like a slow-motion avalanche of condensing gases. The Himalayas, Andes, and Rocky Mountains become vertical laboratories. There, different elevations experience different stages of atmospheric collapse simultaneously. Desert regions, despite their reputation for extreme temperatures, actually resist atmospheric liquefaction more successfully than expected. The dry air and thermal mass of rocky terrain provide slight advantages in maintaining gaseous atmospheric conditions. Areas like the Sahara and Gobi deserts become unexpected refuges. Breathable atmosphere persists there for weeks or months longer than in more temperate regions. 2 weeks after Earth loses its solar heating system, The first patches of sea ice begin forming across the planet's ocean surfaces. But this isn't the familiar seasonal ice formation that occurs in polar regions during winter. This represents the beginning of permanent ocean freezing. It will eventually transform Earth's water-covered surface into a solid sphere of ice, spanning from the Arctic to the equator. The freezing process begins predictably in Earth's polar oceans. There, seawater temperatures drop below the freezing point of salt water, roughly 28 degrees Fahrenheit, compared to 32 degrees Fahrenheit for fresh water. The Arctic Ocean develops its initial ice shell within days. The Southern Ocean around Antarctica follows closely behind. But as global temperatures continue their relentless plunge, ice formation spreads toward temperate and tropical oceans. These regions have not experienced freezing conditions in millions of years of geological history. Ocean currents create fascinating patterns in this global freezing process. The Gulf Stream, that massive river of warm water flowing from the Caribbean toward Europe, continues carrying heat northward. This happens even as surface temperatures drop below freezing. This creates zones of delayed ice formation where warm, deep water prevents immediate surface freezing. The North Atlantic develops a complex pattern of ice and open water. Thermal currents battle against atmospheric cooling in a struggle that determines which areas freeze first. Within 6 months, even tropical oceans begin developing surface ice coverage. The Pacific waters near Hawaii and the Caribbean Sea start their transformation from liquid paradise to frozen wasteland. These warm water regions resist freezing longer than northern oceans, but they cannot indefinitely withstand the cosmic cold that has replaced Earth's normal energy balance. Ocean temperatures that once supported coral reefs and tropical marine life drop toward the freezing point of seawater. The complete ocean freezing process requires roughly 2 to 3 years. Ice coverage extends from polar regions toward the equator and from surface layers down to ocean depths. The deepest parts of the ocean, protected by the thermal mass of billions of tons of water, resist freezing longest. But even these deep water refuges eventually succumb to the relentless cold radiating downward from frozen surface layers. As Earth's atmospheric temperature drops below -200 degrees Fahrenheit, something unprecedented in our planet's history begins occurring. The very air starts snowing out of the sky and accumulating on the ground like cosmic frost. Nitrogen, which makes up 78% of our atmosphere, begins condensing directly from gas to solid crystals. These crystals accumulate on every surface, from mountain peaks to frozen ocean ice. Earth essentially starts growing a new kind of snow. It is atmospheric snow, composed of the gases we once breathed. Nitrogen frost doesn't behave like water-based snow that melts when temperatures rise. These atmospheric crystals only sublimate back into gas at temperatures above -210 degrees Fahrenheit. Those conditions no longer exist anywhere on Earth's surface. Instead, nitrogen accumulates in layers that build up week after week, month after month. These layers create deposits of crystallized atmosphere that could eventually measure feet or meters thick. This happens in areas where atmospheric circulation concentrates the falling gases. Oxygen follows nitrogen in this atmospheric precipitation parade. It condenses into pale blue crystals when temperatures drop below -218 degrees Fahrenheit. These oxygen crystals create their own unique frost patterns. They often form beautiful geometric structures that would be breathtakingly artistic if anyone remained alive to appreciate their alien beauty. The irony becomes profound. The oxygen that once sustained every breath taken by every animal on Earth now decorates the planet's surface as ornamental frost. It lies in a landscape too cold to support any breathing organism. Different atmospheric components create distinct crystalline layers as they condense at different temperatures. Argon, representing about 1% of normal atmosphere, forms its own frost layer at -309 degrees Fahrenheit. Even tiny atmospheric components like carbon dioxide, water vapor, and trace gases create their own unique frost signatures. They do this as they rain out of increasingly thin air. Earth's surface begins resembling a geological cross-section. Different atmospheric layers can be distinguished by their crystalline structure and chemical composition. Wind patterns, where they still exist in the thinning atmosphere, create fascinating drift formations of atmospheric snow. Valleys accumulate thick deposits of nitrogen and oxygen frost. Elevated areas remain relatively clear. Mountain slopes develop their own unique frost patterns as gravitational flow concentrates crystallized gases in natural collection areas. In a world where even the atmosphere has frozen solid, volcanic regions and geothermal hot spots become Earth's final oases. These thermal anomalies create bizarre microclimates where steam clouds rise through air so cold that the moisture instantly crystallizes. It turns into fantastic ice sculptures before falling back to Earth as exotic snow. Yellowstone's geysers, Iceland's hot springs, and volcanic regions around the Pacific Ring of Fire become the last places with liquid water. Everywhere else, water exists only as solid ice. Volcanic eruptions during this frozen period create some of the most spectacular phenomena in Earth's history. When molten lava at 2,000 degrees Fahrenheit contacts atmosphere at -200 degrees Fahrenheit, the temperature differential creates explosive steam generation. This instantly condenses into towering ice formations. Volcanic eruptions essentially become Earth's largest ice sculpture factories. They shoot columns of superheated water vapor that freeze into elaborate crystalline monuments. This happens before the erupted material can return to the surface. Hot springs that once provided relaxing vacation destinations now serve as Earth's final liquid water reserves. These geothermally heated pools remain unfrozen as long as underground heat flow continues. They create small pockets of liquid water, surrounded by landscapes where even the air has solidified. Steam rising from these thermal features creates localized weather systems. Water vapor cycles through evaporation, condensation, and crystallization in patterns unlike any weather Earth experienced during its solar-powered era. The contrast between geothermal areas and surrounding frozen landscape creates temperature gradients so extreme they generate their own unique atmospheric phenomena. Hot springs produce steam that rises through subarctic air. This creates miniature storms where water vapor transitions directly from gas to solid crystals. These thermal oases become surrounded by rings of exotic S formations. These rings grow more elaborate with each eruption of geothermally heated water vapor. Certain volcanic regions maintain pockets of breathable atmosphere where geothermal heating prevents atmospheric condensation. These areas become Earth's final refuges where gaseous nitrogen and oxygen persist in their normal atmospheric ratios. Any hypothetical survivor seeking the last places on Earth where breathing remains possible would need to locate active volcanic regions or hot spring areas. Underground heat creates microenvironments that preserve atmospheric conditions resembling those that once covered the entire planet. These geothermal sanctuaries represent Earth's final gasps of atmospheric normalcy, tiny islands of habitable conditions in a world where the very air has frozen solid and fallen like snow across landscapes. These landscapes once hosted breathing creatures under blue skies, warmed by a star that no longer exists. 3 to 5 years after our cosmic exile began, Earth achieves a milestone. No planet in our solar system's history has ever reached it. We officially become an interstellar object. Our world crosses the invisible boundary where the sun's gravitational influence once ended. We enter the vast emptiness between stars like a refugee fleeing a homeland that no longer exists. We've graduated from being a runaway planet to becoming a genuine cosmic orphan. We have no stellar parent to call home. The transition into interstellar space happens without fanfare or obvious landmarks. There's no cosmic border checkpoint or welcome sign reading "Now entering the void between stars." Earth simply continues its relentless journey at 67,000 miles per hour. The gravitational fingerprints of our former solar system fade into cosmic background noise. We become one of the rarest objects in the universe. We are a planet wandering freely through the galaxy without any stellar allegiance or gravitational master. Interstellar space proves to be even emptier than the vacuum between planets in our former solar system. Matter density drops to less than 1 atom per cubic centimeter. It is so sparse that Earth encounters less material during an entire year of interstellar travel than a single breath contains. We're essentially surfing through cosmic nothingness. We have only the faint gravitational pull of distant stars providing any sense of direction or destination. The temperature differential between our frozen world and the surrounding interstellar environment becomes negligible. Space itself maintains a background temperature of -455 degrees Fahrenheit. It is only slightly colder than Earth's surface by this point in our cosmic journey. Our planet begins to reach thermal equilibrium with the universe itself. It becomes a cosmic ice ball whose temperature matches the baseline coldness of empty space. We've achieved perfect harmony with our new interstellar environment. Except this harmony represents the complete absence of energy exchange that once made Earth a dynamic, living world. Navigation becomes meaningless in this cosmic desert. Without the sun's gravity to define orbital mechanics or planetary relationships, Earth simply travels in whatever direction momentum carries us. The closest star to our former solar system lies 4.24 light-years away, a distance that sounds deceptively manageable. Then you calculate what it means for a planet traveling at Earth's current speed. Even maintaining our breakneck pace of 67,000 miles per hour, reaching the vicinity of Proxima Centauri would require roughly 40,000 years of continuous travel through the cosmic void. That's twice as long as all of recorded human civilization. It makes our potential stellar rendezvous a journey measured in geological rather than historical timescales. To put this cosmic road trip in perspective, consider this. 40,000 years ago, humans were just beginning to develop agriculture and permanent settlements. The pyramids of Egypt would be built and crumble into dust multiple times over during our journey to the nearest stellar neighbor. Ice ages would come and go on Earth's surface. That is only if any ice remained unfrozen in the interstellar cold that has already claimed our world. This represents the ultimate test of patience. It plays out in a universe where even the concepts of patience and impatience have become irrelevant. It is a frozen planet carrying no conscious observers. The mathematics of interstellar travel reveal just how isolated Earth has become in cosmic terms. Light from Proxima Centauri takes 4.24 years to reach our former solar system location. But our planet, traveling at roughly 1/10,000th the speed of light, requires 40,000 years to cover the same distance. We're essentially attempting cosmic travel using the slowest possible method. We carry gravitational momentum inherited from our former orbital velocity around a star that no longer exists. During this 40,000-year journey, Earth would pass through regions of space. They contain matter densities, radiation fields, and gravitational influences completely different from anything experienced during our 4.6 billion years of solar system residence. We might encounter interstellar dust clouds, gravitational anomalies from nearby stellar objects, or cosmic radiation levels. These could alter our planet's surface chemistry in ways impossible to predict. Earth becomes an unintentional space probe carrying frozen samples of solar system materials. It moves through interstellar environments that no planetary body has ever experienced. Even if we somehow manage to survive this 40,000-year journey and approach Proxima Centauri's neighborhood, there's no guarantee our cosmic exile would end. While the odds remain astronomically small, physics allows for the theoretical possibility. Earth might eventually encounter another star's gravitational influence during our cosmic wandering. If our trajectory happens to carry us within the gravitational reach of a suitable star, our planet could potentially be captured into a new orbit. Earth would essentially get adopted by a stellar parent willing to accept a refugee world. Earth would carry the frozen legacy of a solar system that no longer exists. The gravitational capture process requires extraordinarily precise conditions. It makes winning the cosmic lottery seem probable by comparison. Earth would need to approach a star at exactly the right angle, exactly the right velocity, and exactly the right distance. Earth would need to be slowed down enough for gravitational capture. It must happen without being pulled directly into the star or slingshot past it into continued exile. The orbital mechanics involved are so delicate that even minor variations in approach trajectory could determine whether Earth becomes a new planet or remains a cosmic wanderer. Red dwarf stars offer the most realistic candidates for potential stellar adoption. They represent roughly 75% of all stars in our galaxy. These smaller, cooler stars maintain stable energy output for trillions of years. They possess gravitational fields capable of capturing planets within habitable orbital ranges. A red dwarf star could theoretically provide Earth with a new home. Geothermal energy from our planet's interior, combined with modest stellar heating, might create surface conditions less hostile than pure interstellar exile. The habitable zone around a red dwarf star lies much closer to the stellar surface than Earth's former orbit around the Sun. If captured by such a star, our planet would need to settle into an orbit perhaps 10 to 20 times closer than our former distance from the Sun. This proximity would subject Earth to stellar radiation, gravitational tidal effects, and possible atmospheric interactions. These could dramatically alter our planet's surface conditions. The ice covering our oceans might begin melting in equatorial regions. Polar areas might remain frozen, creating a world with climate zones unlike anything Earth experienced during its solar-powered era. Even successful stellar capture wouldn't guarantee Earth's return to habitability. In the most optimistic survival scenarios, Earth becomes humanity's ultimate generation ship, a planetary-scale spacecraft carrying a small population of survivors through interstellar space for potentially tens of thousands of years. Unlike the sleek starships of science fiction, our vessel would be an entire frozen world. It would be powered by geothermal energy and whatever technology could be salvaged from a civilization that never planned for permanent exile from its home star. The logistics of maintaining human survival during such an extended cosmic journey challenge every assumption about long-term space travel. Generation ships typically envision carefully planned missions with predetermined destinations and engineered life support systems. Earth's forced exile offers none of these advantages. Any surviving human population would need to develop self-sufficient communities capable of maintaining technology, producing food, recycling air and water, and preserving human knowledge. They would do it across hundreds of generations without any prospect of reaching a destination that could support normal planetary life. Underground colonies built around geothermal energy sources would become humanity's final cities. Subterranean civilizations that might eventually forget they once lived on a planet's surface under open skies warmed by natural sunlight. Children born during Earth's cosmic exile would grow up in artificial environments powered by their planet's internal heat. They would learn about stars and sunshine from historical records rather than personal experience. These underground settlements would need to maintain technological capabilities sufficient for deep drilling, energy generation, food production, and atmospheric recycling. They would do it across timescales longer than any civilization in human history has managed to survive. The psychological challenges of permanent interstellar exile might prove more difficult than the technological ones. Humans evolved as planetary creatures accustomed to daily cycles, seasonal changes, weather patterns, and the security of living on a stable world. That world was orbited by a dependable star. Generations of humans living aboard spaceship Earth would need to develop entirely new cultural adaptations for psychological survival. This would happen during a journey with no predetermined endpoint. There would be no guarantee that their descendants would ever find another habitable world. The preservation of human knowledge and culture during such an extended exile would require careful curation information across hundreds of generations. The most likely outcome of Earth's cosmic exile involves permanent wandering through interstellar space. It happens within our galaxy's gravitational framework. While our planet will probably never escape the Milky Way's overall gravitational influence, we're destined to become a permanent nomad within the galactic community. We become a planetary refugee carrying the frozen remains of our former biosphere through cosmic neighborhoods that have never hosted life and probably never will. Our galaxy's gravitational potential acts like a cosmic fence. It keeps most objects, including runaway planets, from escaping into the even emptier space between galaxies. Earth's current velocity is impressive by planetary standards, but it falls far short of the galactic escape velocity required to break free from the Milky Way's gravitational embrace. We're essentially trapped within our home galaxy. We have no specific stellar destination or orbital destination to define our cosmic journey. The galaxy offers plenty of room for permanent wandering. With 400 billion stars spread across 100,000 light-years of space, Earth could wander for millions or billions of years. It could do it without encountering another stellar system. We might pass through interstellar dust clouds, gravitational anomalies, and cosmic radiation fields that gradually alter our planet's surface chemistry. But the fundamental trajectory of eternal wandering would continue regardless of these minor environmental variations. Galactic rotation adds an interesting wrinkle to Earth's long-term fate. Our entire local neighborhood, including our former solar system and all nearby stars, orbits the galactic center every 225 million years. Even as Earth wanders through interstellar space, we remain part of this cosmic carousel that has been turning for billions of years. In a sense, we're still riding the same galactic merry-go-round we've occupied since our solar system formed. Except now we're wandering freely through the space between the conventional seats. We are no longer strapped into our former orbital position. Over cosmic timescales spanning millions or billions of years, Earth might eventually encounter gravitational perturbations. They could alter our wandering trajectory. Close encounters with massive stars, passage through dense interstellar regions, or gravitational interactions with other cosmic objects could redirect our path through the galaxy. But these course corrections would simply change the specific route of our eternal wandering. They would not provide any realistic prospect of finding a new stellar home capable of supporting planetary life. Earth's most probable fate involves becoming a permanent galactic wanderer. It is a frozen planet carrying the crystallized legacy of 4.6 billion years of planetary evolution through interstellar space. This continues until our galaxy itself eventually merges with neighboring galaxies in the cosmic future. When Earth's surface becomes uninhabitable, humanity's final refuge lies not in the stars, but beneath our feet, at depths of 6 to 10 kilometers underground. Geothermal heat maintains temperatures warm enough to support human life. The last cities of human civilization would need to be carved from solid rock. These wouldn't be cozy basement shelters or comfortable subway tunnels. They'd be massive engineering projects rivaling the construction of entire metropolitan areas, except they'd be built in environments more hostile than the surface of Mars. The deepest human-made excavations in history reach barely 12 kilometers below ground. They were achieved by Soviet drilling projects that required decades of effort and cutting-edge technology. Creating livable spaces at such depths would demand excavation techniques beyond anything currently available. It would involve the removal of millions of tons of rock. It would also require maintaining structural integrity under pressures that could crush conventional construction materials. Each underground city would essentially require hollowing out mountain-sized caverns in solid bedrock. It would need to prevent catastrophic cave-ins. Geothermal heat sources provide the only realistic energy foundation for these deep settlements. But tapping into this heat requires precise location near active volcanic regions or tectonic zones. This is where Earth's internal energy reaches closer to the surface. This geographic limitation restricts potential underground city locations to areas like Yellowstone, Iceland, the Mediterranean volcanic regions, and the Pacific Ring of Fire. Places where human survival depends on building communities literally on top of the geological forces that could destroy them. The construction timeline for such underground cities would require decades, even with unlimited resources and perfect cooperation. Mining operations would need to proceed slowly to avoid triggering seismic instability. They would also need to install ventilation systems, water management infrastructure, and structural supports capable of withstanding geological pressures. The pressures increase by roughly 1,000 pounds per square inch for every kilometer of depth. These cities would represent humanity's most ambitious construction projects ever attempted, under the most desperate circumstances imaginable. Living conditions in these deep refuges would resemble something between a mining operation and a space station. Every cubic meter of habitable space would be carved from solid rock at enormous energy cost. In a world where solar panels become useless decorations and wind turbines freeze into motionless sculptures, human survival depends entirely on energy sources. They must operate independently of weather, atmosphere, or cosmic conditions. Nuclear power plants and geothermal installations become humanity's only lifelines. They are the sole technologies capable of generating electricity during permanent cosmic winter. Civilization transforms from a diverse energy ecosystem to a streamlined system running on just two power sources. Nuclear reactors possess the crucial advantage of fuel independence from external environmental conditions. Uranium and thorium reserves stored in underground facilities could power nuclear plants for decades or centuries. They could provide steady electrical generation regardless of surface temperature or atmospheric conditions. The radioactive K that drives nuclear fission operates according to physical laws. It is completely unaffected by cosmic catastrophes. That makes nuclear plants the most reliable long-term power source for underground human settlements. Geothermal energy extraction becomes exponentially more important. It is the only renewable energy source still accessible during permanent winter. Deep drilling operations to access underground heat reservoirs would need to operate continuously to maintain power generation. They would require constant maintenance of equipment under extreme conditions. Geothermal plants located near underground cities could provide both electrical power and direct heating for residential areas. They would use steam distribution systems. The electrical grid supporting underground human settlements would need complete redesign for maximum efficiency and redundancy. Every watt of generated power becomes precious when no backup solar or wind generation exists. Energy distribution systems would operate more like spacecraft electrical networks. In those networks, power failure means immediate life support crisis rather than temporary inconvenience. Electrical storage through massive battery installations becomes critical for managing power fluctuations and maintaining backup capacity. Energy rationing would become fundamental to underground society organization. Every electrical device, heating system, and lighting installation would operate under strict power allocation protocols. Designed to maximize survival duration of stored fuel supplies, citizens of underground cities would live in an energy-conscious civilization where electricity consumption decisions directly impact community survival prospects. Food production in underground human refuges would require completely artificial agricultural systems. They would operate without soil, sunlight, or natural weather cycles. Hydroponic farming becomes humanity's primary food production method. It grows plants in nutrient-rich water solutions rather than soil. It is supplemented by LED grow lights that replace the solar radiation no longer available on Earth's frozen surface. These underground farms would operate more like biological factories than traditional agriculture. LED agricultural installations would consume enormous amounts of electrical power. They provide the light spectrum needed for plant photosynthesis. Growing enough food to support even small human populations would require LED arrays. They would consume megawatts of power continuously. This creates direct competition between lighting for food production and electrical power needed for heating and life support systems. Energy allocation between agriculture and survival systems becomes a constant balancing act, with life or death consequences. Crop selection for underground agriculture would focus exclusively on calorie-dense, fast-growing plants. They provide maximum nutrition per unit of energy invested. Potatoes, wheat, soybeans, and other staple crops would dominate underground farming, while luxury foods like fruits, spices, and vegetables that require extensive growing time or specific environmental conditions would become extinct from human diet. Dietary variety becomes a casualty of survival necessity. Water recycling achieves critical importance in underground agricultural systems where every drop must be reclaimed and reused indefinitely. Hydroponic systems would need to operate as closed-loop water cycles. In this cycle, irrigation water, atmospheric moisture, and even human wastewater gets processed through filtration and purification systems. It returns to crop production. Water loss through any mechanism would directly threaten both agricultural output and human hydration needs. Seed preservation and genetic diversity management become existential challenges for underground agricultural systems. Maintaining viable seed stocks for multiple crop varieties requires controlled storage conditions. It also requires careful genetic management. This prevents inbreeding depression in plant populations. Underground farming communities would need to function as botanical arcs, preserving the genetic heritage of agricultural crops that sustained surface civilization while adapting these plants to growth under artificial conditions. Underground human settlements would operate as planetary-scale space stations. Every breath of air must be recycled. Every drop of water must be reclaimed through closed-loop life support systems. These systems would be more complex than those aboard the International Space Station. The atmosphere inside these settlements would become a precious, finite resource. It would be managed through sophisticated filtration and recycling technology designed to maintain breathable conditions. This could last for potentially thousands of years without external input. Oxygen generation would depend entirely on artificial processes. No photosynthesizing plants would exist on Earth's frozen surface to replenish atmospheric oxygen. Underground communities would need electrolysis systems that split water molecules into hydrogen and oxygen. They require substantial electrical power, but they provide the only method for generating breathable air. This would happen in environments completely isolated from Earth's dying atmosphere. These oxygen generation systems would operate continuously as the breathing apparatus for entire underground cities. Carbon dioxide scrubbing becomes a life or death engineering challenge in sealed underground environments. Every human exhale adds CO2 to air that cannot be refreshed through atmospheric exchange with the outside environment. Chemical absorption systems using lithium hydroxide or similar compounds would need to operate continuously. This prevents carbon dioxide poisoning of the underground atmosphere. The waste heat generated by these life support systems would actually provide beneficial heating for underground settlements. This creates integrated life support and heating networks. Air circulation and atmospheric management would require sophisticated ventilation systems designed to distribute fresh air throughout underground complexes, while preventing the formation of dead air zones where carbon dioxide could accumulate to dangerous levels. These ventilation systems would operate more like the respiratory system of a massive organism. Underground cities would breathe through mechanical lungs powered by electrical fans and atmospheric processing equipment. Atmospheric monitoring becomes a critical safety system in underground settlements. Air quality directly determines survival prospects for entire communities. Oxygen levels, carbon dioxide concentrations, humidity, temperature, and air pressure would require constant measurement and adjustment. These systems would rely on automated controls capable of responding to atmospheric changes faster than human operators could detect problems. The arithmetic of underground survival proves brutally unforgiving when calculating how many humans could realistically survive in geothermal refuge settlements. Even optimistic engineering scenarios suggest underground cities could support populations measured in thousands rather than millions. This represents a human civilization reduced to perhaps 0.1% of current global population. These tiny communities would face the challenge of maintaining human culture, technology, and genetic diversity. Their populations would be smaller than most modern towns. Genetic bottleneck management becomes a critical concern for such small human populations. Inbreeding depression could threaten long-term survival within just a few generations. Communities of several thousand people would need careful genetic record keeping and population management. This maintains sufficient genetic diversity for healthy reproduction across potentially hundreds of generations. Living in underground exile. These settlements would function as human genetic preservation programs. They are designed to prevent the extinction of our species through genetic collapse. Social organization in underground survival communities would necessarily evolve toward high levels of cooperation and resource sharing. Individual survival depends entirely on community success. Traditional economic systems based on individual wealth accumulation would become irrelevant in these environments. Every person's contribution to community survival becomes essential for group persistence. These societies might develop social structures more resembling space mission crews than conventional civilian communities. Technology preservation and knowledge maintenance would require deliberate cultural efforts. This prevents the loss of scientific and technical knowledge across generations who never experienced the surface world that created modern technology. Underground libraries, educational systems, and apprenticeship programs would need to maintain expertise in engineering, medicine, agriculture, and manufacturing. They would do this without access to the industrial infrastructure that originally supported these knowledge systems. These communities would become the guardians of human intellectual heritage. Cultural evolution in underground settlements would face unprecedented challenges. Human societies would adapt to permanent artificial environments with no natural cycles, weather patterns, or seasonal changes. These factors have shaped human culture throughout history. Children born underground would develop entirely new cultural relationships with concepts like nature, weather, and outdoor space. These concepts would exist only in historical records and stories. These small communities would represent new experiments in human social evolution. They would develop cultural adaptations for life in environments no human society has ever experienced. They would become the seeds of a potential post-catastrophe human civilization, carrying the biological and cultural heritage of surface humanity through cosmic exile. After exploring 7 chapters of cosmic catastrophe, it's time for some reassuring news from the universe's physics department. The scenario we've been investigating ranks among the most unlikely events in astrophysics. The instant, complete disappearance of our sun. Stars don't simply vanish like cosmic magic tricks. They're bound by fundamental laws of physics that make sudden disappearance about as probable as gravity suddenly deciding to work in reverse. Or the speed of light taking a coffee break. Stars represent some of the most stable, long-lived objects in the universe. Our sun has maintained consistent nuclear fusion for 4.6 billion years, converting hydrogen into helium with the reliability of a cosmic timepiece. This stellar stability emerges from a delicate balance between gravitational collapse trying to crush the star inward and nuclear fusion pressure pushing outward. This equilibrium has proved so dependable that Earth's climate has remained stable enough to support life across geological timescales. The physics governing stellar behavior provide multiple safeguards against sudden disappearance. Even if nuclear fusion somehow stopped instantly, our Sun contains enough thermal energy to continue shining for roughly 30 million years. As it slowly contracts and cools, stars don't have off switches. They're more like massive furnaces that take millions of years to burn through their fuel supplies. Even after the fire goes out, the gravitational energy alone that holds our Sun together represents enough power to keep Earth warm for thousands of years. No known physical process can cause a star to simply cease existing. Black holes don't erase stars. They consume them gradually over time scales measured in millions or billions of years. Antimatter annihilation could theoretically eliminate stellar matter, but the universe contains virtually no antimatter. Any antimatter encounter would produce spectacular radiation signatures rather than quiet disappearance. Even the most exotic theoretical physics scenarios would affect entire regions of space-time rather than targeting individual stars. The conservation of energy principle provides the ultimate protection against stellar vanishing acts. While instant solar disappearance remains impossibly unlikely, our Sun does face a genuine existential crisis scheduled for roughly 5 billion years in the future. This represents the opposite of vanishing. Instead of disappearing, our star will dramatically expand and brighten as it transitions into what astronomers call a red giant phase. This stellar midlife crisis will pose very real threats to Earth's habitability. Though fortunately we have about 5 billion years to prepare for the cosmic inconvenience, the red giant transformation begins when our Sun exhausts the hydrogen fuel in its core after approximately 10 billion years of steady fusion. With the central nuclear furnace running out of easily accessible fuel, the star's core begins contracting under its own gravity, while simultaneously heating up. This gravitational compression triggers hydrogen fusion in a shell around the depleted core, creating a more energetic fusion process that causes the Sun's outer layers to expand dramatically. During this stellar expansion phase, our Sun will grow to roughly 100 times its current diameter, while becoming about 2,000 times more luminous. The star that currently appears as a bright point in our sky will swell to encompass the orbital paths of Mercury and Venus, becoming a cosmic giant that dominates Earth's sky like a wall of nuclear fire. The increased solar radiation will heat Earth's surface to temperatures exceeding 2,000 degrees Fahrenheit, hot enough to melt lead and vaporize any remaining water in Earth's oceans. The red giant phase lasts roughly 1 billion years. During this phase, our bloated Sun will pulsate irregularly while shedding mass through stellar winds. These winds carry away significant portions of the star's outer atmosphere. These stellar winds will create beautiful planetary nebulae, glowing shells of ionized gas surrounding the dying star. They will also reduce the Sun's gravitational influence on the solar system's planets. Earth's orbital distance might actually increase as solar mass loss weakens the gravitational bonds holding planets in their current positions. The ultimate fate involves our Sun ejecting its entire outer envelope into space, leaving behind a white dwarf star roughly the size of Earth, but containing about 6% of our Sun's current mass. Unlike the fictional instant solar disappearance, real variations in solar activity do occur and have measurable impacts on Earth's climate systems. Our sun operates more like a variable brightness light bulb than the perfectly steady energy source it appears to be from Earth's perspective. Solar output fluctuates in predictable cycles that can influence global temperatures, weather patterns, and even technological systems across our planet. The most well-documented solar cycle spans approximately 11 years and involves dramatic changes in solar magnetic field activity. During solar maximum periods, our sun's surface becomes covered with dark sunspots, regions where intense magnetic fields temporarily reduce surface temperature and energy output. Paradoxically, these cooler sunspot regions coincide with increased overall solar activity, including solar flares and coronal mass ejections that actually increase the sun's total energy output by small but measurable amounts. Solar minimum periods represent the opposite extreme, when sunspot activity nearly disappears and solar magnetic activity reaches its lowest levels. During these quiet periods, solar radiation decreases by roughly 0.1% compared to solar maximum conditions. While 0.1% sounds insignificant, this small variation can influence Earth's climate patterns over decades or centuries. This is most noticeable when multiple solar cycles align to create extended periods of reduced or enhanced solar activity. The most famous example of extended solar variation occurring the Maunder minimum from roughly 1645 to 1715. Sunspot activity virtually disappeared for 70 years. This period coincided with the Little Ice Age in Europe and North America. Average temperatures dropped enough to freeze rivers that normally remained liquid year-round. It also caused crop failures that contributed to social and economic disruptions across multiple continents. While solar variation alone didn't cause the Little Ice Age, it likely contributed to the cooling that affected global climate patterns. Modern solar cycles continue influencing Earth in ways that range from subtle to dramatic. Solar flares can disrupt satellite communications, GPS navigation systems, and electrical power grids through electromagnetic interference. This can overwhelm sensitive electronic equipment. The aurora borealis and aurora australis become more frequent and visible at lower latitudes during periods of high solar activity. Charged particles from solar storms interact with Earth's magnetic field to create spectacular light displays. While our sun enjoys protection from internal disappearance mechanisms, the universe does contain cosmic phenomena. Some are capable of affecting or destroying entire stellar systems from external sources. These cosmic catastrophes operate on scales so vast and energetic they could potentially impact our sun and solar system. The probabilities make these scenarios among the least likely disasters in our cosmic neighborhood. Gamma-ray bursts represent the most energetic events known to occur in the universe. They release more energy in 10 seconds than our sun will produce over its entire 10 billion-year lifetime. These cosmic blowtorches result from the collapse of massive stars into black holes or the collision of neutron stars. They create focused beams of radiation that can sterilize planets across thousands of light years. If a gamma-ray burst occurred within our galactic neighborhood, it could strip away Earth's ozone layer. If the radiation beam pointed toward our solar system, it could trigger mass extinction events. Fortunately, gamma-ray bursts require extraordinarily specific conditions that make them cosmic lottery events with astronomical odds against occurrence. The nearest known gamma-ray burst candidate lies over 7,000 light-years away. The probability of such an event occurring with a radiation beam pointed precisely toward Earth remains vanishingly small. Even if such an event occurred, it would likely damage Earth's atmosphere rather than affecting the Sun directly. stars prove remarkably resistant to external radiation that would devastate planetary atmospheres. Supernova explosions represent another potential external threat to our solar system. The probabilities are so low they barely register as realistic concerns. A supernova occurring within 25 to 50 light-years of our solar system could potentially deliver enough radiation to affect Earth's climate and atmosphere. A supernova within 10 light-years might cause significant damage to planetary life. However, no known supernova candidates exist within this danger zone. Stellar evolution timescales make such events predictable millions of years in advance. The most exotic external threats involve theoretical scenarios like vacuum decay bubbles expanding at the speed of light. False vacuum collapse events could alter the fundamental constants of physics, or collisions with strange matter objects like quark stars. These represent the cosmic equivalent of winning the anti-lottery. They are events so improbable they exist primarily as theoretical curiosities rather than realistic threats. Perhaps the most reassuring aspect of these external cosmic threats is their detectability. Unlike the instant solar disappearance scenario we've been exploring, real cosmic catastrophes provide advance warning measured in years, decades, or millennia. Gamma-ray bursts, supernova, and other high-energy cosmic events produce observable signatures. Modern astronomy can detect them from vast distances. This provides plenty of time for any civilization capable of space travel to relocate or develop protective technologies.